and we're doing formal proofs, continuing on what we did last time. And I don't think they're so bad. If you got the purple table where you can do things without for alls and exists, and then you have these rules that allow you to take off exists, take off for alls, and then do purple table kind of stuff, and then put them back on. In fact, it's a little more complicated because sometimes, the purple table says if you have this as an object, a thing, then you can do these with it, and that could have a for all on it. So you can do purple table before you take them off. So it's a balance of take them off when you need to take them off, and the nuance is that when you take them off, you have to remember that how they're there, right? You can't take off an exists and put back on a for all, right? Because a for all is a bolder statement. Just because something one thing exists doesn't mean it's true for everything, right? So that's the nuance. And so what are our rules? Well, I'm pretty sure that when sort of the standard George sort of thing is to have these sort of subroutines, and when you're within this sort of piece, you're allowed to do this and this. And I found it kind of confusing and didn't really learn it, so don't quote me on it. I like to have each line kind of remember everything that's needed. So from one line, you know where you're going. And so we're throwing in these extra symbols. So, for example, when you remove the exists, then you don't put in, when you remove a for all, you put in a free variable, right? A variable doesn't have any quantifiers. And so then free variables are assumed you can put a for all back on. While when you remove the exist, you have to use a symbol. Here I'm putting a little sub exists on them so that you can't put a for all back on them, right? Similarly, there's this weird thing about, maybe it's not up here. When you're doing deduction, if you're assuming, oh yeah, this is the class that doesn't have chalk. I had some in my bag. I wonder if I still have some in my bag. No, none left. So if you assume alpha of x, now which x are you're referring to, right? And it's subtle because in some ways we want to put a for all on the outside, but not while we're within the deduction. So while you're within the deduction, it will have some symbol that says you're inside. Yep. No, I think we'll be fine. Thanks. So here are two situations. If the x came from an exists or you're within a deduction, then you're not allowed to add the for all, right? The other thing is when you're removing the exists, if there's a free variable already floating around, right? You've already removed its for all. So here, in this line here, we're removing this exists y, but there's this free variable floating there. What that's saying is there exists the y, but which y it is could depend on the value of the x. So then I'm saying use this Strodom notation to say, remind you that the y depends on the x, right? And then So yeah, so then that tells you, then that makes it, I don't know. There's this other little rule that when can you put the exist in? Well, if you know that alpha is true for some term, remember a term is just anything representing an object, then you can put the exists on unless that term depends on an x, which is already has a for all on it. All right, so there's all these little rules, and I'm pretty sure that if I needed to memorize all the rules just before a test, I might be able to do that, right? Question mark. But I certainly know in my life I won't remember them all, right? And so what I rely on is kind of understanding what each line means and saying, oh yeah, I can go from this line to this line. I kind of get the rules, right? So these examples, in fact, I was surprised that most of the examples that are here are examples that we did already when we were doing the game. And I kind of threw up proofs quickly, the formal proofs quickly, and didn't, said, well, we'll do it later. So now we can redo them. And one of the things I was doing a couple of weeks ago and then did some more of on Thursday was, instead of doing the proofs line by line, because I found that kind of confusing because I didn't know where I was going and how it related to my intuition, we're bouncing around a little bit more in the proof, because I don't know, then I can see where we're going. All right, so I didn't modify this proof, so it doesn't bounce around, but all right, so here is our statement. What is our oracle assuring us? She's assuring us that if you give me any object in the universe, it could be a banana, doesn't matter, you give me any object, if that object is human, then that object is mortal, right? And the oracle is also assuring us that there's something called Socrates. We don't know, it's just some object called Socrates. And Socrates has the property that this object is human. So then it follows that Socrates is mortal, right? And of course, they were doing this a long time ago, right? So first, right, our goal is to prove we're assuming two things, and we need to imply one thing. Oh, this is where I would have set up the deduction, right? Setting up the deduction is we're assuming A and B, and our goal is to prove C, right? So we assume A and B, we separate the A and B using the separating rule, right? So we effectively have two oracles, right? The A oracle and the B oracle. What's the A oracle saying? Says something about all objects, right? So now it's a for all. We can remove the for all. It turns it into a free variable, right? And then our second oracle tells us something about Socrates. Then we do modus ponens, and then we're done, right? So that was pretty boring. I'm not sure why we did that again. Everybody get that? This is, in fact, the classic, well, I call it classic. It's when I was thinking about how do you remove them and how you put them back, these for alls and exists, the key application is when one order of the quantifiers implies another order, right? Sometimes you can switch the order, and some directions you can't switch the order, right? So what is this? This one says there's one Marilyn Monroe. There's one object Y that works for every X, right? And so then we want to prove that every X has a y. Why does every x have a y? Well, if there's one y that works for every x, then each x has at least that y. Right? Everybody follow that? So here we're condensing, right? I'm using this notation. We remove the for alls and exists, and we get here free variable. We get a fixed object that works for free variable, right? And here what we get is exists the first function from boys to girls that works for all free variable boys, right? So here, how do we do our formal proof? Well, first, I guess I didn't do a deduction. We assume the left-hand side, right? And then, what am I saying in this little note down here? I guess before I put the little arrow, I had a prime. So this means the little arrow at the bottom, right? Here I'm assuming something, right? So any free variables need to be marked. But we don't have any free variables, right? Everything is quantified. If anybody doesn't get what I'm saying, holler, right? So if we had, here we're assuming the left-hand side, and if it had a free variable, we would have to be careful, but it doesn't, all right? So then we remove the exists. So now it's saying we have one fixed object, right? Then we remove the for all with the free variable, right? And then we start putting them back in. Here, the exists is a term, so we can say there exists somebody. And then we have a free variable x, so we can put it back, right? Everybody buy that? And then we have deduction. All right, so then when I first saw that, I panicked. I said, man, that was too easy, right? And we want to say go the other direction. This is just doing the game. Do we need to, everybody have the game? Oh, this is doing it at a game, kind of trying to connect it to the game. I don't know how useful that is. So now we're going to try to go the other direction, right? Why I panicked is because I knew you can't go in the other direction. This is saying every x has a y, doesn't tell me that there's one y that works for every x, right? Every boy loves somebody. Well, it doesn't mean there's a central work, right? So the statement, everybody agree that this is false, right? So our proof was so easy last time, so we have to make sure we can't do it the other direction, right? We assume the left, then we remove the for all, making the x a free variable, right? And then we remove the remove the exists, making it an exists variable, right? And then we have a free variable x, so we can put the for all back, right? And then we can put the exists back, and we're done, right? Everybody's right. And then you say, well, that's a bad proof, right? So then we emailed George and said, dude, what are you doing to us? And he says, oh, no, you didn't read my book. And I said, it's true, I didn't. All right, so then we have to see, what are we doing wrong, right? And in the way I'm talking about what we did, anybody see what we did wrong? Which line is the first one that's a mistake? Line 4 is a mistake. Line 3 is still fine, right? But line 4 is a mistake. And so what do we have to do? We have to say that the y is a function of the x, right? and so line 4 now is fine, and then line 5 is now fine. I look at line 5, I read line 5, and I say, what does it say? Right? It says what I want, right? For every x, well, we can plug it in this function y that exists, and we get some y that works. Right? Everybody see that I can still read, I can know what this line means as when I do the steps. Each time I can check and say, yeah, I still have the right meaning. Right? And then we say, that's all good. All right, so now can I put the exists on? And I can't, right? I can't because there doesn't exist one y. The y depends on the x, right? And that's why we have this rule. Everybody good with that? All right, so now here's just a longer chain, and so here we kind of condensed it to say, well, let's first take all the for alls, right? All the for alls are free variables given us by some adversary. So I just banged in red free variables for the for alls, right? And then what am I banging in for the exists? Well, I have to think for each exists, what does it depend on, right? On the left here, make sure I have my left right. The first exists doesn't depend on anything, right? The y1 doesn't depend on anything. The y2 depends on the x1, right? Now you might say it depends on the y1, yeah, but that's in our control, so we're not worried about that. The y1, the free variables aren't in our control so much, right? So everybody say we got that, right? Well, but over here, the x's, all the exists, the y's depend on both of them, right? And so then you have to think, well, can I do the implies this way? Can I do the implies this way? Well, turns out we can do the implies this way because if something is constant, it's still a function, right? One example of a function over here that depends on things is a function that doesn't depend on things, right? Depending kind of gives you, right? So that's just what we're saying. And so what do? Well, we rip off the first exists, right? We rip off the for all, we rip off the for all, we rip off the second exists. And see here, what we have is just that line that I was saying that we're kind of condense it to, right? Just by ripping them off. And then what can we put back? Well, we can put the exists back because here, this is a this is an object that exists. It could depend on the free variable, but there's not a for all out here already, right? If this was a term that depended on a variable that had a for all, then we couldn't add it, right? But it doesn't depend on a for all, so we can add the exists, right? And that subtlety again is where, am I going to remember the rule or am I going to remember the meaning of this and the meaning of this, right? And so then you can add the for alls back, right? Any questions about this? Does it feel kind of scary? A little bit, right? Oh, this is just the game again. We can do them if you want. All right.